So the other thing we can do is,
when the whole humanoid industry started to boom, we started to realize that our cons for industrial robots actually became a pro for humanoids.
And you want to talk about the Archimedes Drive and the inspiration behind it.
All right.
All right. Morning, Thibaud. Welcome to the Soft Robotics podcast.
Thank you, Scott. Thanks for having me.
Yeah.
So I really look forward to the conversation that we'll have today. I know we're in a beautiful scenery in Munich, Bavaria, in Germany. So it's as a European, it's feels a little bit like home, but it's nice at least for you to kind of see it as well a little bit.
You might think we're in a beer garden, but actually we're not. We're between two halls at the Automatica 2025 trade show. And what's your impression so far?
It's really good. So I think this is the third time that we're here. Mm-hmm. So, in the early days of the company, I came here actually myself as the very first person to kind of set up a small booth. And every single time we come back, our booth gets a little bit bigger. Yeah. And you definitely see it progress from how it was 6 years ago to where it is today. Mm-hmm. And for us, I think it's one of the most important trade shows for us to go to.
Oh, yeah. It's the same for us. Yeah. I think the first time we were here was like 2006 or something like that. So it's like 10th or 12th trade fair, and it's the biggest one for us. Mm-hmm. So it's the most important one, and there's a good reason why. And it is really the biggest automation trade fair in the world. Yeah. And you can see that when you walk these different buildings. Yeah. So the one thing I noticed walking around the buildings, being a robotics guy, I saw lots of robots out there. Yeah. Every booth doesn't have a robot; they have like lots of robots, like the cobots, the normal industrial robots. But when you walk through there, you probably weren't counting robots; you were counting like servos.
Exactly. Yes. I was counting servos and I was counting actuators. Well, it's funny that you say that, because every time someone comes to our booth, how do I know that person is a potential serious partner or client is where they look at the robot. Yeah. So we have a Delta robot at our booth, and we have our actuators up top, and it's doing some pick and place manipulation on the bottom. And when people come by and the first thing they do is look at the bottom, then I know they're less interesting than when they come by and the first thing they do is they look at the top. Yeah. Because then I know right away that they're interested in actuators and drive systems.
How it works.
And how it works, yeah, exactly.
Because, the Delta robot is kind of a magic robot. You look at it, it's like, well, wait a minute, where are the motors? Yeah. And they're way up top. It's a parallel kinematic mechanism. And the whole idea is it's not carrying any of the actuators, so it can be really, really fast. Now, do you know what inspired the Delta robot?
No, I don't, actually.
Visit to a Swiss chocolate factory.
Interesting.
The best ideas are always inspired. So, yeah, it goes back to the 80s.
Can I use that quote, by the way?
Oh, yeah. Absolutely. And so, again, it's the idea of packaging problems that you have when building robots is that it's one thing to make a kinematic mechanism. The other thing is like, how do I make the darn thing move? Yeah. And then the complexity is there when people realize that motors are big and bulky, and you don't want to put it at the very end of the arm because now you're reducing the payload. You want to move it to the front, which needs some weird transmission system. And also the actuators have had to improve over the years. So to go way back to the 1980s, robots had ball screw drives, which were linear actuators, which I've always said it's rather silly to take rotational motion, turn it into linear motion to then convert back to rotational motion. Why not go right to the source? Yeah. And because back then the motors were not energy dense enough. They didn't have a support. That was the only way you could do it.
Makes sense.
It improves. You can start to get the actuators to stretch. Now, the same thing, of course, I really like the humanoid bot strategy from all aspects of robots. And again, that's the problem, is that we can very easily make a mannequin or something like that looks like very much like a human. It's like almost perfect representation. It's like, oh, I can make that thing move. Oh, we'll put motors in there. Okay, get started, And then you begin to realize how complex it is. And how do you get the motor torque you need? How are you able to deliver? How do you make it safe? Which is the biggest thing. So everyone asks me, when am I going to get a humanoid bot in my house? And they think the answer is like, well, when it's mechanically sound, when the AI is good enough. And the answer is like, it's neither. It's when it's safe.
Yeah, I agree.
And if it's not safe, so it'll be in the factories ahead of time, because we can make factories safe for humans and humanoids, because we just end up cording them off and you can't get into it. But in the house, it's a little bit different. And even then in the factories, we'd like to co-locate humans with the humanoids. They need to be near each other and not hurt one another. And so that's where drive units come in. And again, I had mentioned servos before, and servos are more or less like one half of the actuator. It's the motor, and the actuator, I like to say, it's just a fancy word for a motor that has a bit more, because you get the spinny part, and then you've got this transmission that has to take the high RPMs you have there and then get it down to what you need to make sure it's sort of a safe speed for your bot.
Yeah.
So how fast do actuators, or let's say servos or motors, typically spin at? How many RPM?
Well, it really depends on which motor, of course.
Yeah,
let's say 5,000 up to 10,000 RPM, somewhere around there.
Yeah. So we're talking thousands of RPM.
Yeah.
Okay. But then if you look at even an industrial bot, the normal speed, they might be 1 revolution per second would be like a top speed. So that's like what, 60 RPM, or so we're talking about a factor of anywhere from 10 to 100 difference. And 2 reasons. One, you don't want it to be so fast. And second, when you go through a gearbox, what happens?
The ratio, there's a reducer, an increase in torque.
Increase in torque, exactly. So you don't have to have a super powerful motor.
Yeah.
All you have to make sure is what comes out at the end is there. So at some point you have to have a transmission mechanism. No. All right. So
well, of course, it's more nuanced than that. Of course, it's the holy grail of robotic actuation is direct drive.
It's direct drive, exactly. And there's no such thing as a direct drive. They do have something called a QDD, which is
I fully agree with you on that. And I think if we go a little bit later in our conversation about why I think our technology is very interesting, I think it'll enable QDD.
Right.
So
and that's quasi, as I might say in German, which means like almost a direct drive.
Yeah, almost. Yeah.
I think the technical definition is when the gear ratio was like less than 10.
Yeah.
So it becomes very, very close.
Yeah.
And so you want to now there's a lots of ways of being able to, we're saying gear ratios. So that means people think, transmission. Lots of kinds of transmission. So we can rattle them off.
Yeah. Go ahead.
What is kind of like the oldest transmission that known to man?
It's a standard planetary drive.
Planetary goes back to
so it's
Archimedes, doesn't it?
Back to the old days, yeah. So I'm Dutch, and I always say that the old windmills that you see all over our country, those use standard planetary transmission systems.
Exactly.
And I think it's quite poetic because those systems allowed us to actually reclaim our country from the sea.
Exactly.
So it shows you the power of such a system.
Exactly. And so for those who don't know, it's called the planetary system because you have the central shaft, which is the sun, and it spins really, really fast. And then you put a bunch of these gears around there that look like planets that are orbiting around there, and then takes a ring gear on the outside and makes that go very, very, very slow. Yeah. So that's a way of doing the reduction. It's all very nice. But there's a couple problems with it.
Yeah.
And one of them is
weight, volume,
backlash.
100%.
And then depending on what the gear ratio is, it's just not back drivable. Yeah. And the other is, of course, if it's not back drivable, then you start getting these safety issues you start talking about. So
transparency is very, very important for safety.
Exactly. And for control.
And for control.
That's the other thing. That what an actuator is, it's like a motor, a gearbox, and it's a control system. That's like the part I left out of it. So it's like everything is built into there. So you can control the thing. You want speed control, position control, force control. You need to know all that to be able to do it. So to get the humanoid to work, we have a lot of things at odds. That we want to have a lot of torque. Like that, a lot of torque is not going to be safe. Yeah. We can't have a high, and if you want a lot of torque, you need to have a high transmission ratio. High transmission, you don't have the torque transparency. It means it's really hard to control. So you've got to get it down there, which is why the Holy Grail is QDD. Yeah. So that's one drive. Now the other thing is since backlash is a problem, and something having backlash means it's really hard to get that position control. It's sloppy. It's like you want it to go there, but it ends up going there, or you change direction and it doesn't move when it's supposed to because the gears don't engage. There's always that little slop.
Exactly. There's a little bit of play in the system. Yeah.
So what's the solution? Typical solution?
You would go for a harmonic drive.
Harmonic drive. Exactly.
Or let's say a strain wave gear to do the technical term.
Yeah, that's another term. Yeah. It's kind of funny. It's like intentionally making the two gears and not be exactly the same gear ratio, that they kind of mesh inside of each other, that you've got a couple of them are always there. It's a complex mechanism. Yeah. The back drivability is there. It's more costly. Yeah. So that's one. Another type of transmission that I see several looking at are like cycloidal.
Cycloidals, exactly. Yeah. So cycloidals have been used in the industrial robots for many, many years. And you're really seeing, that's what I see now is you're starting to see the transition from industrial robots into humanoids, because cycloidals offer some unique benefits. Mm-hmm. Like for example, the backlash, it has a lot better backlash characteristics than a standard planetary gearbox. It's a lot stiffer. Yeah. So stiffness pretty much is, you're holding the input and how much does the output deflect when you're given a force on it. And cycloidals are very, very stiff with regards to that as well.
Now, what a lot of people don't realize about gears is that, you look at them and it's like, wow, they're like the big, massive, strong things. They're absolutely incredible. But the reality is that all the forces of torque are being transmitted through just a couple of teeth. It's not being distributed around the whole thing. The planetary gears try to distribute that a little bit, so you have like more than one tooth engaged at the same time. But in the end, you get a lot of wear and tear in there. And if one of those teeth break, that's it, right?
Yeah, I completely agree. And if you emphasize it a little bit more, if you look at robotics and the application, you realize that a robot makes a cycle. So you never have continuous rotation in the gearbox. That means that wear usually happens only on a few teeth, because those are the ones that are continuously engaged.
That's true. That's true. That's the other thing. Because your range of motion is limited to something like that. Yeah. Whereas when you put it in like a transmission of your car, it's constantly cycling pretty much in the same direction for a very long period of time, hundreds of thousands of kilometers. So those are the kind of transmissions that everyone sort of thinks of right now. If you go down the checkbox, they're like, oh, okay, consider this, and this. They all have their benefits. So, might be volume, might be costs, complexity you're going to put in there, where it has backlash, the transparency, and everything else. But there's a new kid on the block. There is a new kid on the block.
I think to make your story a little bit more complete in terms of transition, you were talking about rotary actuators. What we're also seeing is linear actuators.
Yes. Yeah. Oh, yeah. That's the other thing. And that, so they also have like a pretty bizarre transmission system in there, which is known as like a planetary roller screw.
Yep.
It's a linear analog of the planetary gear system, where you're trying to take rotation and then convert it not into slower rotation, but to now into linear movement. And you need to have these planetary roller screws, and might be like this long or that long. They have a certain length to them, and you need more than one. Usually, you need about a dozen of those things. They're pretty costly, very, very high precision, and that will add probably the majority to the cost of the actuators right now. And there's also a potential supply issue with that.
Yeah.
So the idea of a linear actuator, again, a humanoid, everything is rotational. So why are we talking about a linear drive? You don't need to put in there. And the idea is that, well, in some cases, we want to have a lot of torque. We're going to put a linear drive in there, and you have to convert that rotary motion to linear motion. And then it kind of gets caught on a pin here. And then you use that to make you articulate around a particular giant. So it has a lot more literally moving parts in there, a bit more complexity, but there are pros and cons. There are places where it kind of makes sense for packaging reasons, for forced torque reasons that you're able to get in there. And a lot of times it's just natural, because a linear actuator fits kind of very neatly in your arm, because your arm is long and skinny. And if you want to put a rotary actuator in there, it's like, oh, it doesn't quite fit right.
It's really bulky.
Well, let's say, in my case, it wouldn't fit. You could fit them in there.
Maybe it'll work, yes.
Exactly. So those are different cases. But at some point, you still need to take high-speed rotary motion and slow it down a little bit, and be able to come up with a robot which is going to be safe, that you're able to control correctly. And I was looking at different kinds of transmission systems. And you want to talk about the Archimedes Drive and the inspiration behind it?
Sure.
And I guess we can a little bit say, it's like, think about planetary gears and how they work. It's very similar. It's motivated that way.
Yes, it is.
And explain it, because I think I
No, great.
And also,
great. No, Scott, sounds good. I think I can explain our technology. So I think you summed up the current landscape of existing technologies quite well for gearboxes. And of course, we want to introduce a new solution.
Yeah.
And we think our solution, checks mostly all the boxes if you look at humanoid actuation. But before I'll go into that, of course, I want to talk about our technology and what makes us unique. I think the biggest differentiating factor between us and existing systems is that we don't use gear teeth. So we rely purely on traction or friction to transmit torque.
Right.
So how does that work? Before I really get into the details of our drive, think of a train. Think of the train wheels on a train. You have the weight of the train pushing on the train wheels. Those train wheels are on the track, and the train moves forward. And the train only can move forward because of the normal force of the train pushing on the wheels multiplied by the friction coefficient, and that generates enough traction for the train to move forward. And we use the exact same principle within our drives. So how does our system look, and how does our system work? Well, it looks like, the transmission systems of old, so the planetary drives.
Mm-hmm.
So we looked at a planetary configuration, but instead of having, your standard planets, so the gears on the outside that are toothed systems, they're hollow rolling cylinders. And those cylinders are a little bit oversized for the space that's available. So what does that mean? When we put the system together, we shrink some parts, we expand some parts, we put everything together, and we let it come back to its standard shape.
Right.
And that allows for those cylinders to kind of under a little bit of compression. So they act like springs.
Mhm.
Therefore, let's say the elastic expansion of the steel that's acting as a spring, multiplied by the friction coefficient of the steel and steel contact, allows you to transfer force through traction.
Right. Right. And you get a little deformation on there, which means your contact area is not the theoretical line of contact, but there's actually a little bit more.
There's a little bit more, yeah.
There's a little bit more of that.
There's a little bit more, yeah, because it's under compression. You're talking about a couple microns.
Yeah.
But yeah, it's not a direct line contact. It's a little bit more than a
A
line.
little bit more. Now, and anyone that's in any sort of engineering and goes into designing transmissions, if you got the gear ratios, you always look at like the number of teeth that you have on there to figure out like from one gear to another. And if you want to change the gear ratios, a lot of times it means you need to change the number of teeth that are on there. The thing is, as you increase the number of teeth that are going to be on a gear of a certain size, the teeth have to get smaller and smaller because that's just geometry. It's like the more you put in there, you can only get the depth so much. And so a lot of people will look at it and say, oh, it looks like you have 0 teeth. And the first time I looked at it, it's like, no. What actually happened is that if you think about it, it's not that you went to 0 teeth. You went to like an infinite number of teeth, because what ended up happening is the teeth get so small, you didn't see it. So you got to look at the limit the other way.
No, I agree. And, if you really zoom in on a contact patch and you look at it with, a microscope, then you realize that the surface isn't smooth. Mm-hmm. And those, that's what you say are the infinite teeth that we have in our system.
Yes, exactly. Yeah. Exactly. So a lot of times, people, if you look at the problem the wrong way, thinking, oh, it's 0. And I'm really saying, okay, 0 and infinity are kind of related somehow. If you look at the other way, then that means your formulas start to work out. They start to make sense. Yeah.
It makes sense. No, I agree. And I think you got onto another interesting point, and that's gear ratio.
Right.
So, that's one piece of the puzzle for our technology is transferring torque through traction. Mm-hmm. But of course, how do we get a gear ratio from the system? Yeah. And specifically get a high gear ratio, so above 20:1, to use for robotic actuation in a small package. And for us to be able to do that, we use something called the compound or the Wolfram or the split principle. So if you look at one of our planets, you realize that there's a step in the diameter of one of our planets.
Yeah,
and that small step, so the difference in the diameter of the outside and the inside allows us to generate a gear ratio. So the way that works, it's pretty complex. So I would advise you to kind of Google it yourself to see how the Wolfram principle works. But we have, let's say, multiple rings inside the drive that are fixed to the ground, and we have our output ring that's rotating.
Right.
And that output ring, the inner diameter of that output ring is a little bit bigger than the ones that are ground. And that coincides exactly with that step in the planets. Mm-hmm. So allowing us to have that step allows that ring to move at a very slow speed. If you would kind of imagine the system as a theoretical level, you would take that output ring and you realize that ring has the same inner diameter as what we call our ground ring fixed to the world, then the system will not move. The moment it becomes a very small difference, it moves very slowly. And the bigger that difference, the faster the output will move with a constant input speed, of course. So it's a bit more of a complex system, but that allows us to have a very large variety of gear ratio within the same volume and weight of the system.
Okay, sure. Now, again, one of the properties that you have is that because you don't have any teeth, you don't have to worry about teeth breaking over torque. So a lot of times the size of the teeth you have may not be dictated by the gear ratio you want to have, but by the torque you have to transmit. So you have to make sure the teeth are not going to fail. But a lot of systems will always end up at some point having an over torque situation where something's going to break and that becomes a disaster. You need to have maintenance. Now, in your case, if we overstress the system, what happens?
It slips.
It just slips.
It slips. Yeah. So it acts like a slip clutch.
Yeah.
And I think that's very, very interesting. Like if I take a step back and I look at traditional transmission systems or traditional gearboxes, they always give 3 torque values. So they give your nominal torque. That's the one that you can usually test on for life. They give you your maximum repeated torque. That's the one that you can continuously operate at. And they give you your peak torque, which is the absolute maximum torque that the system can handle. And if you go over that, well, then the system fails.
Right. In one way or the other.
And
we would like it to fail safely.
Exactly. And that peak torque is always 2 to 3 times higher than your maximum repeated torque. Mm-hmm. So systems, as the way we see it, are always over-designed because you have to be able to withstand those, once in a lifetime or a couple in a lifetime emergency events.
Right. Yeah. Right. Now, that might be something if you're putting it into more like a transportation mechanism or something like that. But when you start having robots where people are going to be around them, then you have to be a bit more cautious of like, oh, how much I over-design this thing? I don't want it to fail. Or what if a person is nearby and they get struck by the robot? You'd like the system to somehow fail or shut down. There's 2 ways that we can have them shut down. One, we hope the robot's smart enough that it just knows to stop. And there are a lot of safety systems in industrial robots that will kind of do that. But unfortunately, in some cases, the robot stops and then the person is pinned and no one can move the bot because the bot is like, oh, I've got to stop moving at this point. And that also becomes an issue. So the big bots, because of their high gear ratios, are not back drivable. So if you're pinned, you can't move it.
Yeah.
If you want to have the humanoid bots, we want to be able to get out of a situation like that. We can't rely completely on software because software will always have glitches and fail. So there's a digital solution that people try for. But it would be nice to just have an analog solution where if all things go south, there is one way that you can get out. And that is to make sure it cannot hit you at too much of a force. And if you do get pinned, if it's on top of you, you can take a joint and just push it and it goes away. So are you going to demonstrate that?
Yeah, exactly. So that's what makes us unique. So, I think we're the only drive system on the market that has inherently, a mechanically over torque protection, as we call it.
Yes.
So, I was going back on, you have your repeated torque and your peak torque. Well, for us, we don't have peak torque. We have something called slip torque. And the moment you go over that slip torque, the drive slips. But then afterwards, you go back into the operating regime and the system works again. So it's kind of an inherent mechanical collision resistant safety mechanisms built inside of our drive.
Okay, and you're going to prove that?
Yeah, definitely. So if you want, you can have the honors of hitting it with a hammer. So what I'm doing is I'm moving the drive so you can have a nice whack at it.
See if you like this. I'm trying to push on it. Oh, I can. Am I overdoing?
You can actually slip it.
I can actually do it. Of course, the other thing we can do is. And it's going to move.
It's going to move.
So at some point, it will definitely be able to lift me up. And then if I apply too much force, it's just going to stop.
It's going to stop.
It's going to stop, which is what you want. So you can design that to be whatever is required for the safety.
Yes.
And the other thing is, like, if I had my hand down here and you were going the other way, there's no way you can really pinch me down there too hard.
Agree.
Then I can I can get my hand out.
Get your hand out. Exactly.
Well, part of that there was back drivability, which you just saw, right? Yeah. So I can back drive the motor. But if that motor is locked somehow, then I've got the opposite.
To really
be able to get it to go up.
Really lift
so that's something that's pretty important. Now, so the criticism is going to be, all right, I've got my robot completely calibrated and I'm measuring my joint position at the motor. So I'm counting revolutions of the motor, and by revolutions of the motor, I should be able to infer what the position of my arm is. And now suddenly this thing has slipped. So I've lost my zero reference. Do I have to go back out there and recalibrate the whole thing all over again?
Yeah, so that's where you use an output encoder.
Okay, so that's exactly it. So the answer to the question is that you don't measure on the input, you measure on the output.
You measure on the output, All right. So you assume that the system as a whole is just one system. And instead of measuring at the input with the motor, we look at the output of the drive.
Yeah. In some ways, measuring at the output is the safer way of doing it. Even though a lot of systems measure on the input, there's like an implicit assumption about what's going on between the input and the output. And if something breaks in between there, you don't really know where you are. So you are literally measuring where it's more important. That's where you need to have the information.
Exactly.
Now, you would compare some of that to sort of what's going on with your motor behind it, the scenes, or the control system, to get an idea of whether the torques and everything are where you want them to be, whatever the path is. So a lot of times you do want both of that information.
I agree.
But the most important one is if you want your elbow at 45 degrees, let's measure at the elbow and not measure at some actuator or motor someplace else.
And you're seeing that in humanoids. So most of the humanoid actuators are actually measured at the output. For accurate position control and for just sensing exactly where the arm is at a given moment in time.
Right. So slippage is not an issue. That's fine. And again, it makes sure it's going to be safe in a variety of different situations, digitally and also in the analog. Okay. So what kind of interest are you starting to see for this approach over all the others? Because this is completely new.
It's completely new. Agree. It's completely new. We are drastically different because of the fact that we don't use gear teeth. So you're starting to see, multiple things which are interesting, specifically for humanoids. So like you said, safety is very, very big. So our system is inherently collision resistant or collision safe, and we can design it to slip at a specific torque. Therefore, if there's a specific safety concern regarding pinching your hands, for example, that's something that we can solve mechanically from the system itself. So that's good. The second one brings you back to the very first point that we were talking about. That's backlash. Our system has zero backlash. We have continuous rolling contact of all the rolling cylinders about the drive, and we have no slack or play because we don't have gear teeth. That means that our backlash is 0, and it's 0 throughout the full life of the drive. So what does that mean from a robotics perspective? That means that it is very, very controllable. Mm-hmm. So you know exactly where you can position your output exactly where you want it to be.
Yeah. And that's important. And sometimes it doesn't make sense. It's like, wait a minute, it's able to slip and it has no backlash because that's basically what backlash is. It's when you get a point of slip.
Yeah.
The thing is, you don't have like a continuous slip in there. You have almost a step function on that, which is what you want. Whereas, yeah, the hysteresis that you see in a lot of other systems just drives the controls guys crazy.
No, I agree. It's funny that you put hysteresis. If we measured the hysteresis of our drive. Normally a normal hysteresis curve kind of has an S profile. Mm-hmm. Around the 0 area, that's the gradient is very high, and then all of a sudden it becomes a lot stiffer towards the end because of that change in hysteresis inside of the drive. For us, it's very different. It's a straight line. Mm-hmm. Because our contact mechanism is the same across the whole torque spectrum until you slip, and then you have full slippery the system.
And you don't get any of those surprises. And I've learned myself over the years, like some of the prizes you get a robot and you want it to draw a circle. And you go down there and it draws some ellipse. You're like, oh, wait a minute. I programmed it to draw a circle. And why is that? It's because if I've got a pen on my robot industrial arm, a lot of this movement is being done with the first axis right here. So like it's going back and forth this way. So I start here, I move over to there. Now I have to change direction to come back. And at the moment you change direction, suddenly you get that backlash where it takes a fraction of a movement of the bot to be able to engage and go in the opposite direction. The problem with the first joint is it's really far away out here. Now you probably play soccer, right?
Football, as we call it here in Europe, yes.
Is it easier to kick the ball in the goal from the penalty box or from midfield?
From the penalty box.
Right. Why?
Because you're closer to the goal.
You're closer. So in other words, your margin of error is very different. You can have a big error there, but it results in you still being able to hit the goal. If you do it from midfield, you have to be right on. If you're just off a little bit, you're going to miss the goal. So the same thing is happening. So if I have a little error in axis 1 and my tool TCP is way out here, it just magnifies it. It becomes really bad. If I've got a little bit of error out here, you don't see it as much, but down here is a problem. So like the history, and of course, this is like the big boy. Yeah. This is the one that's carrying the load of everything that goes on there. And as soon as you try to reverse direction, it won't reverse direction. It keeps going. So what happens to my circle? Comes an ellipse. And this is the bane of all the big robots and everything is trying to eliminate that to get the precision. Yeah. And so as soon as you get rid of that, it's like, this will make the movement and everything a lot easier. So think about it with, any sort of a humanoid bot. The problem is going to be up there in the shoulder. I mean, it's like that's the error there magnifies way out here versus any error you have in the elbow versus or the wrist you have here at the wrist. Yeah. So that's like a brief history of hysteresis and why it could be a problem.
And backlash. No, I agree. It's exactly what you said. An arm magnifies the problems that you have with hysteresis. Mm-hmm. And that's why when you look at standard industrial robots, that's why they always use 2 different types of drives depending on where they're located.
Yeah.
So, we were talking about cycloidal drives, for example. Those are usually used in the base of the robot because they're very high stiffness, have better hysteresis properties, and they can handle that small deviation a lot better, let's say. And the further you go down the robot arm, then you'll start seeing a transition from cycloidals to strain wave gears. Mm-hmm. And the reason why strain wave gears are used is very simple. They're lightweight. So they're the most lightweight solution. And therefore, the grams that you save on the weights really propagates to, limiting the extra torque at the base to be able to lift that.
Right. Yeah. Right. So, sort of talking about these different transmission systems, if I want to buy a Planetary gearbox, I have a lot of options, right?
Yeah.
A lot of suppliers for that. Harmonic Drive, also.
You're starting to see it a lot more nowadays, yeah.
Yeah, but a lot of different suppliers are doing it. And then you have cycloidals. There's also a lot of suppliers. Okay, how many are supplying this drive?
One.
Just one. Okay. So it shows it's kind of new.
Yeah.
The other ones are kind of old school. They're old school a bit. Yes, there's been a lot of improvement in there, a lot of precision that has to go in there. So if you were to compare the cost of that versus, like a Planetary system or strain wave system, or say the detail, the amount of precision that goes into it. And we can also talk about like a Planetary roller screw, which is another thing which is much higher precision. How does the comparison there comes down to not just cost, but manufacturability, the difficulty of doing the precision kind of equipment you would need.
That's a good question. So, of course, cost is leading, specifically when you look at humanoids, where they want to make cost-effective solutions to go into the mass market, and that cost directly drives the cost of the actuator and therefore the drive unit itself. So if you look at our system, and I'll look kind of theoretically on where we would compare in terms of cost for existing solutions. The biggest cost drivers for gearboxes today are the gear teeth. That's by far one of the biggest cost drivers. So how can you manufacture those gear teeth in a very cost-effective way? Let me wait till that guy rolls back a little bit. So how can you manufacture gear teeth in a cost-effective way? They've been doing this for many, many years, but right now they're very much at the limit. So there's always a bottom line of you can't go more cheaper than that because you still have to manufacture the gear teeth. Well, for us, we don't have gear teeth. We don't have to worry about that. So we can, instead of looking at traditional manufacturing techniques for gearboxes, all of a sudden we're looking at bearing manufacturing techniques. And bearings are a lot more cost-effective to produce than gearboxes because they don't have to worry about gear teeth. And that same kind of methodologies we can apply directly to our core components. So once you start scaling, once you really start manufacturing at volume, I think we could be very, very cost competitive.
Okay. And so, like a lot of Planetary, especially strain wave, you need very special equipment for that.
Yes.
Grinding equipment, which there's only a limited number of companies that produce the kind of equipment to do it. I remember after 2010, there was like a shortage on harmonic drives. Yes. If you remember, before 2010, there was a bit of a recession there. Yeah. And all the robot manufacturers were kind of gearing up, literally. Suddenly the economy collapsed. And then we weren't sure if it was going to be a dead cat bounce or something like that. But ever since then, the robotic market just took off. Yeah. So following that, suddenly the number of robots that had to be shipped in that year exceeded what had really happened the other years by almost a factor of 2. Yeah. And there was a shortage of harmonic drives on the market because of the quality that's needed to go in there, the manufacturing. And only a few companies that actually produced the grinding equipment that allowed you to do that. Yeah. So you can have supply constraints on those things. Obviously, it's just not something that you can build in your basement if you want to get the kind of quality and volumes in there. You need a certain degree of sophistication. But the other thing to look at it is that sometimes the sum of the parts is greater than the whole. Yeah. Or in this case, maybe less if you start thinking about, all right, rather than buying a motor and buying a control system and then buying a transmission system, what if we start thinking about designing the whole thing together? Yeah. And not like these Legos that we put together, but something completely together. Yeah, and
an integrated actuator.
Absolutely integrated. Yeah. And you would get a lot of things, I imagine. One would be cost. Yeah. One would be performance. Yeah. One would be better space.
Yeah. Yeah, and that goes back to the quasi-direct drive that we were talking about earlier. Before I dive into that, I thought it was very interesting that you said that, Harmonic Drive was the bottleneck of the industry. Yeah. And it still sort of is the bottleneck of the industry. Because, like you said, there are more manufacturers making strain wave gears, but it's very, very difficult to achieve the quality that the industry requires. Yes. So some can make it and it works fine for, a year, the robots. But then all of a sudden, the performance decreases drastically and you can't use it anymore. So there's a difference between making a strain wave and a good strain wave that can be used for industrial robots.
Harmonic drives aren't just in robots; they are also in EVs. Yeah, yeah. And so a lot of those, they're very demanding. So you just cannot get a strain wave from wherever you want. You have to go ahead and make sure you get the right supplier and sub-supplier to produce those parts. So again, it's precision, it's manufacturing everything right, and then again, it's the integration. So if I was to just say I'm going to take someone's motor over here and take the Archimedes drive and combine them together, I probably would get something that's more of a Frankenstein kind of actuator. Exactly. Now, what are you proposing?
So what we're proposing is a fully integrated actuator, to actually make a quasi-direct drive using our system. So our system looks like a cylinder. It pretty much looks like a metal donut. And you can really easily integrate a frameless motor inside of our drive unit. And that frameless motor, the rotor of that frameless motor, can directly be integrated to our inputs. Okay. And then you have the output, which is an outer ring. And that outer ring also acts as the housing of the system. So you don't need those additional components to make the housing.
Exactly. Yeah.
So it makes it very, very simple to create a full actuator from a drive. And because of the properties of our system, the very nice linearity of the hysteresis curve, the high stiffness of the system, the zero backlash, the high efficiencies at low gear ratio, because of our drive, we would finally be able to, enable quasi-direct drive systems. And that's kind of, the direction where most of these humanoid companies are going towards.
Okay. Are you seeing any traction?
Yes. Yes. So I think we're seeing a lot of traction. I like the word traction, by the way. Very good.
It wasn't intentional.
So the company is about 10 years old. Before I talk about traction, it's kind of explain what the difference is. The company is about 10 years old. So, I, together with 3 others, founded the company 9 years ago officially, but we started working on the idea like a little bit over 10 years. The very early days of the company, we were fully industrial robot focused. And we realized, some robots liked it. Some companies didn't like it. There were things that are nice, like the zero backlash, the high stiffness, but things like slip were a nice to have, but not a must have. And kind of the interfaces, which makes us very good for quasi-direct drives, does not make us good for traditional industrial robots where they just want to bolt on a motor and kind of make a Frankenstein construction. So there were some pros and cons. So they liked it, but they weren't really super excited. Fast forward to about 3 years ago, when the whole humanoid industry started to boom, we started to realize that our cons for industrial robots actually became a pro for humanoids.
Exactly.
So the slip, they absolutely love it. The quasi-direct interface, drive interfaces, they absolutely love it. The high efficiencies that we can achieve at low gear ratios, they absolutely love it. So all our cons all of a sudden became pros, and that added on top of the pros that we already have. So just by on paper and the analysis that we're doing, these humanoid companies are getting very, very excited.
Yeah, and again, a lot of people sort of watching this at home would probably be saying, "Oh, the thing slips. No one's going to buy it for that." And then you begin to realize what seems to be a weakness is actually the strength of the system. It's able to do that.
And if I want to dive a little bit deeper in that, humanoid companies want their actuators to slip.
Exactly. That's why it becomes an advantage.
It becomes an advantage because they want that kind of inherent safety mechanism inside of the actuator themselves.
But still thinking that, okay, so you get that, but you don't want to have the backlash of hysteresis.
Yeah.
And for a lot of gearboxes, it's maybe not a big deal if things are always moving the same direction. So like in an automotive transmission, if you're just going straight ahead, once the gears are engaged, they remain engaged and there's not a problem. With humanoids, you're going to have a lot of fine movement. You may have motor movement, which is just a slight movement this way and a slight movement back. You got to control to get that detail. And if you do it with a lot of normal systems, you will have a little bit of backlash, which makes it like really tricky. And if anyone was ever tried, you probably tried to remote control things, something like that. You get that little precision and you move it a little bit, and darn thing overshoots. And then you try to, and it comes back again because you're trying to figure out when is that thing going to engage right. Now, if you don't have it, your precision becomes a lot better. So that could be also, I would see another upside of not just the fact that you have at some point of a torque that's going to release is going to slip at, but that you do not have the backlash.
Yeah.
And that's the thing that really has to be pointed out. It's not just the slip torque. It's also the fact that you don't have backlash.
You also have backlash. Yeah, it's the combination of everything.
Yes.
So these humanoid companies, people always ask us, what's the one thing that they really like about your drive? And I say, it's not one thing. It's the combination of multiple aspects of our system, like the zero backlash, the slipness, the slip, the stiffness, the cost effectiveness at high volumes. They sum all those parts up. They look at existing technologies on the market. They do pros and cons, and eventually they decide that our technology could be very, very interesting for them.
Right. Especially if you integrate everything, and if you start designing the whole package as one, just rather than thinking of things that you bolt in there, you put them in, you'll have a lot of advantages of scale. So, how cost sensitive are the humanoid bot companies?
Very cost sensitive.
Okay.
There are two things which they care the most about. That's cost and weight.
Yes. Okay. And if you look at a normal humanoid bot, there's roughly 30 structural actuators that are needed to go from the feet all the way up to the head and out to the wrist. And then we have the fingers, which is like, that's something else. And that's going to be a costly part of the structure. Yeah. And let's not count the actuators you need there because they're all over the map as far as that. But for a typical humanoid, you're looking at about 30 actuators in there. And that means if each actuator costs $1,000, my bot is going to cost a minimum of $30,000, not including all the other stuff I have to put on top of that. So is the $1,000 actuator something that is achievable? Is that like the high end or is that the low end, you believe, in the cost of an actuator?
So that should, for the humanoid market, that should be the high end.
The high end, right? You cannot come up with an actuator split. Now, what's the ideal number?
You divide it by 10.
Yes, everyone would like to have it for 100. So at that point, that means the actuators, which will probably always be the most expensive part of the bot, will then be around 3,000 pounds.
Yeah.
And after that, you start summing up the parts, the rest of the body. It's really hard to come up with another $7,000. I mean, it's like, yeah, there's technology that's rather advanced and impressive, but at scale, when you start talking about like the chips that are going to be needed, you can get them fairly low cost sensors, cameras, stuff like that. It's really hard to get up to like $7,000. So if you're able to get it down to that level, you're talking about probably a sub $10,000 bot someday.
Yes.
Now, how soon do you think we will be able to get to a $100 actuator?
It's going to take some time.
Yeah. Okay. Where do you think we are roughly now? What's the? You think most these everything's kind of customized, so they're all spending a bit more than
they are. They're spending a bit more, 1,000 on their drives.
They start scaling right now. Do you think they'll be able to hit 1,000 like this year or next year?
No. So it depends on how much. If they start scaling, then yeah, they'll hit 1,000.
They hit about 1,000.
They'll hit about 1,000 when they start. But the real question is what happens afterwards,
right?
How much volume do they need to make in order to get that €1,000 down to 100 euros? And is it even technically possible to be able to do that?
Yeah.
And that brings me back to kind of that, fundamental inherent problem with existing transmission systems or gearboxes, and that's gear teeth. And those are really driving the costs of actuators. Mm-hmm. The manufacturing of those gear teeth, the complex materials that you use, that there are only a couple suppliers that can actually make them at those quantities with the quality that you require. And that kind of limits the bottom end of an actuator that you can make.
Yeah. Now, if you look at building a humanoid bot, everyone's trying to figure out what is going to be the limiting factor there. Is it going to be, am I going to have enough cameras? Am I going to have enough batteries? Is there going to be a supply shortage of that, on chips and everything else? And then there's something about actuators, and we assume we will be able to build enough motors if we need to do that. And one area that was identified was this planetary roller screw, which is basically for things that are linear drives. And each of the actuators needs about 10 of these things. So that would be quite a bit. And it turns out when you look at the equipment that generates these things, they're not like standard threaded screws that just get pumping out of a machine. They're the machines that are producing things are producing in the order of single digits per hour. Yeah. So it's like, oh my God. And if you want to build a million Tesla bots, and each one of those actuators is going to require about 10 of them, and half of the actuators in Optimus are linear. 14 to be exact, and assuming about 10 there. If you build a million of them, you need 140 million per year to be able to do that, which means you need equipment. And it turns out the equipment that's producing it is producing on single digits per hour. Then you start running the math like, wow, that's going to be a lot of these machines that are going to need to do that. So as you start to scale up, you begin to wonder how big does a factory have to be, how difficult it is. So the reason I'm bringing that up is that, is it a similar issue with that? It's like, how quickly do you believe you could start producing all of the components that are needed for the Archimedes Drive? And are we going to require like a huge factory to be able to work with lots and lots of equipment, or is it something that's able to produce it at much higher rates?
That's a good question. So there are two parts to it. So, of course, our drive is unique, and we have some unique components in there, which is different than anything else on the market today. So we will need to have, let's say, custom machines or modifications of current machines to be able to manufacture those parts. But I think once we have those modifications and we start to really fine tune kind of how you would make them, then we can really easily scale and grow the manufacturing process. And that brings me back to, why I think our drive is cost effective at high volumes. And that's because it resembles a bearing. We've been doing bearing production for hundreds of years now, and we are going to use the exact same manufacturing techniques as bearings. Mm-hmm. So the only thing that we really have to look at what are the bearing guys doing? How can they achieve the volumes? What machines do they use? And what modifications do we need to make on their machines in order to make our parts? And once we get that down, then I think we can scale very, very nicely.
Okay, so you're feeling it's less complex than doing something like a planetary roller screw.
Yes.
So that's going to be a good thing to know. Yeah. Okay, so I think we've covered quite a bit here. Can you think of anything else? Yeah,
so maybe what's interesting is the moment we talk about complete systems and actuators, I think it's good to kind of discuss what I like to say kind of old age robotics, which is your typical industrial robots, and your new age robotics. So, your humanoids or robots that work what I like to call unpredictable working environments. If you would look at old age robotics, their actuators are quite simple. You would have a motor. After a motor, you'll have an encoder. You'll maybe have a brake. Then you'll have a reducer. Then after that reducer, it's the output into the robots. It's a very nice system. And usually if you want to optimize for that, you want to have a very low weight and high precision, So what you'll do is you'll end up with a cycloidal drive or a strain wave gear with a very high gear ratio, because then you can have a small motor and the system becomes light. And, that solution has been used for about 50 years now within the industry, and it's fully been optimized, and it's a great solution for the industrial robots that you see today. Now, if you look at the humanoid industry, then all of a sudden it becomes very different. The moment you take a robot outside of a controlled working environment and start putting it into an environment with people, with external factors that you didn't predict for, then all of a sudden you have to design your actuators very, very differently. You're talking about actuators that can withstand unpredictable collisions, that are inherently safe when they work alongside humans, that are very controllable, and that are able to react very fast to stabilize an inherent unstable system. And then you're starting to realize that the actuators of old are not the same as the actuators of new. They kind of give you an idea. We were talking about quasi-direct drives and the direction this industry is going for. And they're actually, if you're looking at the reducer, they're looking at the complete opposite direction of industrial robots. Industrial robots want high gear ratio, so they can make this motor small. Yep. Humanoids want low gear ratios, so they can have a low reflected inertia to be able to withstand collision events. And they have a low gear ratio, which allows the output to move faster with an input of the motor to stabilize the system. And all of a sudden, when you have to design for a low gear ratio system, your full actuator looks different. You need a bigger motor. And because you have a bigger motor, the system becomes heavier. But since your system also needs to be inherently safe and you need to control it correctly, you have to add an output encoder to the system. You want it to slip as well during collision events, so you have to add an output clutch. Right. You want to know exactly what's happening on the arm of the robot, well, then you have to add a torque sensor on top of that as well. And then all of a sudden you realize that the actuators for humanoids are becoming a lot more complex than the actuators for industrial robots. And that's kind of where the catch-22 comes in. It needs to be cheap. It needs to be sub $100 for an actuator. However, these actuators are becoming more complex than what they're using in industrial robots. So how are they going to solve that? How are they going to bridge that gap?
Yeah, you need a different solution.
You need an inherently different solution.
An integrated solution.
And an integrated solution.
And the other thing that we were talking about safety, we're talking about the safety of the humans around the bots, but we also have to think about the safety of the bot itself. Yeah. So you're going to have these events where it's just going to fall for some reason, because maybe a digital failure or something like that. When an analog system will come in, if your system is stiff and your robot falls down, it's probably going to break something. Yeah. But when it falls down, if it's sort of able to absorb that energy, there's a good chance it's going to be able to stand back up. So there's also another advantage to it.
I fully agree with you. And the conversations I've had with people in the humanoid space, they call it the difference between usable torque and collision torque. Yeah. Specifically, if you start looking at the wrists, the hands, and sometimes the elbows, they're smaller drives because, you have less of an arm, so you need less torque in the system. That means your usable torque is low. But if you collide against something, then your collision torque is very, very high. Yeah. And all of a sudden, if you have to design these drives to withstand the collision torques, then you end up with very big, bulky systems. And they can't do that. So they have to, mass optimize it, make it small for the actual torques that you use in the system. But once you collide into something, it completely breaks. And the biggest nightmare right now within humanoids is the breakage of the hands and the wrist because of the collision of the system. Yeah. And for us, we don't have to worry about that because it just flips.
Mm-hmm. Yeah. Oh. Easy to replace, low maintenance. So I think we've covered quite a bit there. And I want to thank you, Thibaud, for arranging this. The sun's been kind of coming out here. It's going to be rather interesting to see what post-production looks like. Yeah, but thanks. We'd love to do this again.
Definitely. That would be great. Thanks a lot.
Great. Thanks.
Have a good one.